Hello, hello, hello. Okay. So first thing I want to say is I'm sorry about updating the slides for week 9. So if you have downloaded the previous version I uploaded for week 9, the slides are changed. Like there is a little bit change in what chapters we are going to cover for the rest of the class to catch up with the schedule. So now, if you download from e-class the week 9 slides and week 9 with notes slides, they're updated, they're new version. So I'm sorry for updating in mid of this week. This is first of all. Second of all, from today on, all the online classes will be recorded according to a new university policy. So you can find the recorded links later appearing on e-class under each week section. And then, because we're doing both online and in-person lectures, so the office hours are going to be hybrid mode too. So you can go to my office while studying for office hours, or you can attend the office hours during that time period through Zoom link too. Okay, so that's about office hours. All right, so we'll continue to finish the spherical coordinate in triple integration. So last time we talked about this example where we found the limits, 0 and cosine theta for rho, that is the distance from any point on the surface to the origin. Next, we want to find the limits, the integration limits for phi. So we know phi is the deviation from the positive z-axis. So although this angle we know is given from the figure itself as power 4, but our question is, can you find the measure of this angle if this power 4 is not given to you? So basically we know this angle is the angle of the cone, right? So we will be examining the cone equation to see if we can get this angle from the cone equation. So from the cone equation, let me write it here. From this cone equation, we have z equal to square root of x squared plus y squared. So what we are going to do is we translate this equation in x, y, z to an equation in spherical coordinates, rho phi theta. So z is equal to rho cosine phi, if you can see it. And x is equal to rho sine phi cosine theta. So this gets split. Plus y is equal to rho sine phi sine theta in spherical coordinates. So the equation simplifies to the left-hand side remains the same. The right-hand side is rho squared sine phi squared cosine theta squared plus rho squared sine phi squared sine theta squared. Right. So rho cosine theta phi is equal to under the square root, because I have this same thing multiplied by cosine theta squared, this same thing multiplied by sine theta squared, and we know cosine theta squared plus sine theta squared is equal to 1. So under the square root, I have rho squared sine phi squared. So by taking the square root, I have rho sine phi. So there's no plus or minus because rho, I only want the positive on the square root. Rho is always positive, and because phi goes in between 0 and pi, sine phi is always going to be positive. So I have rho cosine phi is equal to rho sine phi. And the two rows, they cancel each other. So in the end, I have cosine phi equal to sine phi. So what angle of phi will give me the same cosine and sine value? It is pi over 4. So phi will be pi over 4. So that means this cone, the angle between the cone surface with the positive z-axis is pi over 4. This is how we get the pi over 4. So let's go back. Here, now we know, okay, this angle is pi over 4. So we know the largest possible value, the angle the phi can reach is pi over 4. So the lower limit for phi is 0 and the upper limit is pi over 4. It will start from the positive z-axis and reach as far as pi over 4. Fine. So the last one, the limits for theta. Theta describes the rotation, like horizontal, the rotation in a horizontal sense. How much of the horizontal space the region can cover. So you know it covers horizontally basically every space. So this is a full round. So theta goes from 0 to 2 pi. So this is how I describe the solid E in blue using rho, phi, and theta. So now I have the triple integral set up. So I just need to integrate rho squared sine phi. So this is an easy integration. It doesn't involve any additional techniques like integration by cross substitution. So I'm not going to show the process. In the end, after evaluation, the result should be pi over 8. So what I want to show you is, given this solid region, how to describe the shape of the region using spherical coordinates. Okay, so if you want more details, you can look here. So how I get the limits for rho. Rho varies from 0 to cosine phi. Cosine phi is basically this part of the surface. And phi will start from positive z-axis and go this way. So the farthest angle it can reach is pi over 4. And theta can go from 0 to 2 to cover the whole 3D solid region. Okay, so this is all about spherical coordinates. So next, the last chapter of 15, the last section of chapter 15 is change of variables in multiple integrals. So this will be actually a summary of all the coordinate systems we're talking about. In 2D space, we have two coordinate systems: polar coordinates, Cartesian coordinates, or rectangular coordinates. In 3D space, we have rectangular, cylindrical, spherical. So this somehow helps us to relate them together. So let's start from the 1D case where we see in calculus 1 or 2. We know in calculus, in one variable calculus, there is some trick called change of variable or substitution. That is, if I am given a single integral, like this is an integration of f from a to b for x. So I don't want the integration to be with respect to the variable x anymore. I want to change from x to u. So let me check if there's any comments from the Zoom. So I want to change the integration variable from x to u. So I write x is equal to, I express x in terms of u. So x is equal to a function of u. So then I want to rewrite the integration from with respect to x to with respect to the new variable u. So if when x is equal to a, the lower limit is when x is equal to a, u is equal to c. If when x is equal to b, u is equal to d, then the same integral can be written as, this same integral can be written as, now it's an integration from c to d. They're the values for u when x takes those two values a and b. And f of x, because x is a function of u, so now f of xu, f is a function of u. And dx, because x is equal to xu, dx is equal to the derivative of x with respect to u, du times du, right? So in the place of dx, I have dx du. So you see, why this is called change of variable or substitution, because previously the integration is with respect to x. Now I have a new integral with respect to the new variable u. So this is called a change of variable. So the question we want to answer here is, what is the counterpart, how to change variables in 2D and 3D integrals. Okay, so now the change of variables in 2D variables in double integrals, that is, I have this double integral, right? I integrate a function f of x, y. But I am not satisfied with this choice of x, y. I want to change from the variables of x, y to the variables of u, v, new variables. So I write x is a function of u, v. I call it x of u, v. Y is a function of u, v. Y, u, v. So geographically, you can see, okay, this is I would rather write this is R, and this region we call it S. To be consistent in our notation use. So previously, I integrate f of xy over this region R. This region R is in the xy plane. Now I change from xy to uv plane, and this region in uv plane will become another region, another shape. We call it S. Okay, this is the change of the integration region after I change the variables from xy to uv. This is one thing. Another thing is, if we define the Jacobian of this transformation, we have a transformation from xy to uv. We define the Jacobian of this transformation as this: partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. And this is a second order determinant. So why we need this, we'll see it later. So you see, x is a function of u, v, y is a function of u, v. Put the partial derivatives of x with respect to u and v in the first row. Put the partial derivatives of y with respect to u and v in the second row, and they will give you the Jacobian. So now, after we have all these, the double integral, the original double integral in xy becomes a double integral in uv. How? F of xy now becomes f of x is equal to, x can be expressed using uv, right? Y can be expressed using uv. And dA, previously dx dy, now becomes the absolute value of the Jacobian times du dv. And previously it's an integration over the region R in the xy plane. And after the change of variable, the integration region becomes S in the uv plane. So what I want to emphasize here is the Jacobian relates like dx dy to du dv. dx dy is equal to the absolute value of the Jacobian times the new variable du dv. This is the significance of the Jacobian. So from this result, we can see, okay, we know when we do double integral, rectangular coordinate, we write dx dy. In polar coordinate, we write r dr d theta. So now we will see why there is an r here from xy to r theta. Find, in this one example, find the Jacobian of the transformation from rectangular coordinates to polar coordinates. Rectangular coordinates, they are xy, polar coordinates, they are r and theta. So basically, I have a transformation from xy to the new pair of variables r theta. And I know their relationship is given by x. If I want to express x in r and theta, x is equal to r cosine theta, right? And if I want to express y in r and theta, y is equal to r sine theta. So the Jacobian, once we have those expressions for x and y in the new variables, we can come up with this Jacobian. The Jacobian is equal to a second order determinant of partial x, partial r, partial x, partial theta. First row, derivatives of x. Second row, the partial derivatives of y, partial y, partial r, partial y, partial theta. So let's find all these partial derivatives. The first one, partial x, partial r, it is cosine theta. Partial x, partial theta, I differentiate this with respect to theta, I will have negative r sine theta. The second row, differentiate this with respect to r, I have sine theta. And differentiate this with respect to theta, I have
old house.
r
And
cosine
Maple
theta.
James Street.
Yeah. So
That's
I found the
that
four
was
partial derivatives.
like that area is where like Lucas
Can you
lives.
still recall how to evaluate the so-called second order
My brother's friend, one of my brother's friends.
How to evaluate this
And around that,
determinant?
sorry, where his parents live.
I need to multiply these two and then minus the product of these two. This is how you evaluate a second order determinant in your applied maybe algebra. So I have cosine theta times r cosine theta minus negative r sine theta times sine theta. Then you write it more compact. Negative r sine theta times sine theta. So this times this minus this times this. So let's simplify this expression. I have r cosine theta squared plus makes a minus. Oh, minus makes a plus. R sine theta squared. So this is like, if I factor this r out, I have just cosine squared plus sine squared. And cosine squared plus sine squared is equal to 1. So it's equal to r. So now we understand why. So the apps, let me write it here. Now you understand why dx dy, according to the following, according to the above result, should be equal to the absolute value of the Jacobian times dr d theta, right? And the absolute value of the Jacobian is absolute value of r. And r is always positive. So that's why we have always seen r dr theta. Okay, so because basically it is a change of variable from rectangular variables to polar variables. So this is why we have this one. Okay, next, so this is 2D case. We go one dimension up to 3D case. The change of variables in triple integral in 3D case. The idea is exactly the same. Just I have one more variable. I have a triple integral of a function of x, y, z. Now I am not satisfied with the choice of x, y, z. I want to go from x, y, z to a set of new variables, u, v, w. So I want to rewrite the triple integral not using x, y, z anymore, everything in u, v, w. So I have the conversion between the two sets of variables x. I express x using u, v, w. I call this function x of u, v, w. I express y in u, v, w. I call it a new function y of u, v, w. I express z in u, v, w. So I use the function z of u, v, w. So in order for the consistency in notation use, I will still change the name of this to r, name of this to s. So in x, y, z, the integration region looks like r. So if I change it to u, v, w, the integration region will be looking like s. I call it s. Okay, and the Jacobian, the important thing is the Jacobian. The Jacobian relates dx, dy, dz to du, dv, dw. So the Jacobian, the idea is exactly the same. Now it's a 3 by 3 matrix. The first row, I have all partial derivatives of x with respect to u, v, w. So partial x, with respect to u, with respect to v, with respect to w. First row. Second row, I put all partial derivatives of y with respect to u, v, w. Third row, I put all partial derivatives of z with respect to u, v, w. Once I have that Jacobian, the original triple integral in x, y, z becomes the integrand f. Now it is a function of u, v, w. So I rewrite x using u, v, w, rewrite y using u, v, w, rewrite z using u, v, w. And dv previously is dx, dy, dz, right? Now it becomes the absolute value of the Jacobian du, dv, dw. So this part remains the same. You always need to find the Jacobian. And it relates, this absolute value of Jacobian relates dx, dy, dz to the new set of variables du, dv, dw. And the integration region goes from the previous region R to the new region after the transformation to S. Okay, the idea is exactly the same. So now we will use this result to find the Jacobian of the transformation from rectangular coordinates to spherical coordinates. Remember, we talked about when we do spherical coordinates, we do not ever forget rho square sine phi d rho d phi d theta. Okay, so now we will see why we will always see this rho square sine phi going with d rho d phi d theta. So rectangular coordinates in 3D case, it's x, y, z, will go from these two new variables, rho, phi, theta, the spherical variables. So we know the equation that relates them is if I express x using rho, phi, theta, I have rho, sine phi, cosine theta. And y, in spherical variables, I have rho, sine phi, sine theta. And z, in spherical variables, I have rho, cosine of phi. So the Jacobian, I put partial derivatives of x in the first row, partial x, partial rho, partial x, partial phi, partial x, partial theta. Second row, everything of y, partial y, partial rho, partial y, partial phi, partial y, partial theta. And last row, everything of z, partial z, partial rho, partial z, partial phi, partial z, partial theta. Inside the two long bars. So I need to find these 9 partial derivatives. So the first partial x partial rho, it is sine phi cosine theta. And the next partial x partial phi, it's rho cosine phi cosine theta. Partial x partial theta, it's rho sine phi times negative sine theta. Put negative sign to the front. This is the first row. And next I work on y's partial derivative. Partial y partial rho sine phi sine theta. Partial y partial phi rho cosine theta sine theta. Partial y partial theta negative rho. Oh, sorry, I don't have the negative now. Rho sine phi cosine theta. And then I work on these partial derivatives. Cosine phi, partial z partial phi is negative rho sine phi, and partial z partial theta is 0. There's no theta component in it at all. So it's like a differentiating constant. So now I need to find the value of this third order determinant. Let me add a new slide. I'm running out of space here. Anyway, let me see if I can write everything here. So I need to find the third order determinant from this matrix. So I observe there's a 0, so I can always start with the row or column containing 0 because it's easier. So I will choose to expand with respect to the last row. So if I choose to expand with respect to the last row, this row here. So what I would do is I have cosine phi. I take cosine phi, right? I take the first element from the last row, and I delete the column containing cosine phi, deleting the row containing cosine phi. Now I have a second order determinant. So it's cosine phi, row cosine phi, cosine theta. This term times this term minus this times this. Times rho sine phi cosine theta minus makes a plus rho sine phi sine theta times rho cosine phi sine theta. And next I take the second element but with a negative sign. So negative makes a positive times 2 plus rho sine phi. And I delete this row, it is in, and this column, it is in. So I have this times this minus this times that for the remaining second order determinant. Sine phi cosine theta times rho sine phi cosine theta. Minus makes a plus. Rho sine phi, this one. Sine theta times sine phi sine theta. And then I take the last element because it's 0. 0 multiplies everything, gives a 0, so I can ignore that. So this is the value of the second order determinant. Okay, so let's simplify this. So I have cosine phi. So inside this I have rho squared cosine phi sine phi cosine theta squared plus rho squared sine phi cosine phi sine theta squared plus rho sine phi times rho of sine phi squared cosine theta squared plus rho times sine phi squared sine theta squared. So what you can see is, okay, this is rho squared sine phi cosine phi, rho squared sine phi cosine phi. So basically, I will have just cosine theta squared plus sine theta squared, that makes a 1. So the first term becomes cosine phi times rho squared cosine phi sine phi. And the second term, I have the same thing. I have a similar thing. So the second term is rho times sine phi times rho sine phi squared. Okay, so see if we can simplify further. So the first term is rho squared cosine phi squared sine phi. The second term is rho squared sine phi squared. Let's write this times sine phi. So you see, I can factor the common term, and what remains is the only different terms in the two terms here. So cosine phi squared plus sine phi squared is equal to 1. So in the end, I have the Jacobian is equal to rho squared sine phi. Okay, so as it's equal to Jacobian is equal to rho squared sine phi, so dx, dy, dv is equal to the absolute value of the Jacobian times d rho, d phi, d theta. And it's the absolute value of this rho squared sine phi, d rho, d phi, d theta. And can I take the absolute value sign off? Because yes, because rho squared is always positive. Sine phi is always positive because phi goes in between 0 and pi. So sine of phi stays positive, stays non-negative. So I can have the absolute value is just rho squared sine phi, d rho, d phi, d theta. So now you can see why. We always say, okay, when you do spherical coordinates, integral, do not never forget rho squared sine phi. So this is the reason. This is actually the Jacobian connecting rectangular coordinates and the spherical coordinates. Okay. So this is how you do change of variable. So let's practice a more concrete example. So use the following given change of variable to evaluate this double integrate y over the region D, where D is the region bounded by the x-axis and the two parabolas. So the change of variable you need to follow is change from xy to uv like this. X is equal to u squared minus v squared. Y is equal to 2 times uv. And this transformation, this change of variable transforms the region D to a rectangle, u in between 0 and 1 and v in between 0 and 1. So previously we talked about how to find the Jacobian relating dx dy, du dv. Another challenge in doing a change of variable is the previous integration region changes to a new integration region. So I'm not going to expand like how you find the new shape of region. Like in this example, it is given. So after the transformation, the region D will be changed to a rectangular region. It's directly given to you. You don't need to bother to find the new shape of the region. So let's just practice. Rewrite the old double integral to the new double integral in u and v. So we have x equal to u squared minus v squared, y equal to 2 uv, right? Like we said, first we need to find the Jacobian. The Jacobian is partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. So the first row Partial x partial u, it is 2u. Partial x partial v is negative 2v. Second row, partial y partial u, it is 2v. Partial y partial v, it is 2u. So evaluating this second order determinant, I have 2u times 2u minus 2v times 2v. So what I have here, I have 4 u squared plus 4v squared, right? Okay, so let's try to rewrite this double integral. I have y dA over d. So right, compactly I write it. Okay, it's over d of y dA. So I want to express everything using u and v. So the integrand needs to change to u and v, and y is given as 2u. So y becomes 2uv for the integrand, and dA becomes what? dA becomes the absolute value of the Jacobian times du dv. And the limits they're directly given, so you don't need to find them yourself. U goes in between 0 and 1, V goes in between 0 and 1, so naturally, because I put du first, the inner limits, therefore U from 0 and 1, from 0 to 1, and the outer limits, therefore V, also from 0 to 1. So I just need to find here the absolute value of the Jacobian, 2uv. The absolute value of the Jacobian is 4u squared plus 4v squared. This is always positive, right? So its absolute value is itself, 4u squared plus 4v squared u d. So this is how you change a double integral into a new double integral in terms of the new variables. So next, the evaluation is easy. So the answer will be equal to 2. So the important thing I want to emphasize here is when you transform from old variables to new variables, the Jacobian, the absolute value of the Jacobian relates these elements, the xy, from the xy to the new variable you need. It will help you set up the new double or triple. Okay, so we need to understand how to find the Jacobian. We need to understand how to evaluate two orders, third order determinant. All right, so this is all about like change of variables. So now you know why we have r derivation. So you can try yourself. When we go from rectangular coordinates to cylindrical coordinates, we will have r dz dr theta. And you'll understand why we have that r there. And you now also understand why when we go from rectangular to spherical coordinates, we have rho squared sine phi d rho d phi d theta. Okay. All right. So this is all about integration. Now we will move on to the last chapter. Actually, chapter 16 is the most difficult part in this course. It's way more difficult than differentiation and integration. So we'll start from the introduction of vector fields in R3, in 2D space, and R2 and R3, 2D and 3D spaces. Maybe you're already familiar with those concepts, so this is not a hard concept to understand. First, the vector field in R2. R2 means the 2D space. Like here I have XY plane is a 2D space. The vector field means I assign to each point in the 2D space XY. Here is a point. I assign a vector to each point. So a function f that assigns to each point xy a two-dimensional vector. So f of xy is equal to a vector z, and this vector depends on the point xy. This point, its coordinates, they're xy, so the x component of the vector is, let's write it p of xy, and the y component, let's write it as q of xy. Or in another form, I can write pi plus qj. So pq here, they are scalar functions. So in the graph, the vector field will be looking like this. At each point, there is a vector. At this point, there is a vector. At this point, I have a vector. So you will see a lot, like a representative of vectors at the selected points. This is the 2D vector field. So 3D vector field is the same thing. I have a function f that assigns to each point x, y, z, a three-dimensional vector. So here, sorry, it should be x, y, z. F of x, y, z is equal to a three-dimensional vector. And the x component, I call it p, y component q, z component r. In another form, I can write this is equal to pi plus qj plus rq. So p, q, r, they are scalar functions. So in the graph, the vector field looks like this. At each point in the space, there is an associated 3D vector. At this point, this is the associated vector. At this point, this is the associated vector. So this is like I assign to each point a vector. This is a vector field in 3D space. So here are some like real life examples. So these two graphs shows the air velocity vector field. This is like the air wing. This is like, it shows each arrow shows the wind speed and direction. For example, in this location, the wind blows in this direction and its magnitude, the magnitude of this vector denotes its like speed. If I have a longer vector, that means the speed is larger at this point. So this graph shows the wind speed and direction in the San Francisco Bay Area. This is for 6 p.m. and this right graph is for 6 a.m. You see, at 6 p.m., this is how the wind blows in direction and in magnitude. And at 6 a.m., the direction changes at each point, right? So these are two perfect examples of 2D vector space, vector fields. Okay, so back to like theoretical and mathematical problems. Let's try to make a graph of a 2D vector field. If f of xy is a vector field in R2, and is given by negative yi plus xj. So first, sketch some of the vectors f of xy. So I want to sketch the vector field. So this is a 2D vector field, so it's on my plane. So maybe I can select some points. Let's select these points. This is the point. This point is x equal to 1, y equal to 1, x equal to negative 1, and y equal to negative 1. So let's find the vectors at these 4 points. The first one, the vector at the point, this point, 1, 0. It is equal to, according to the function, it is equal to negative y, right? Y is equal to 0 and x is equal to what? I plus, sorry, negative y. Negative y is equal to 0, so there's no I component. I will write, if I use this form to denote the resulting vector, it's 0, 1, right? So at this point, the vector is y is equal to 0, x is equal to 1, so 0, 1. So I draw a vector 0, 1 at this point. The vector 0, 1 means the vector is pointing up, like with 1 unit in the y direction. There is no displacement in the x direction. There's just 1 unit of displacement in the y direction. So this is the vector at this point. Next, I try to find the vector at this point. This is x equal to 0, y equal to 1. So according to the given function, y equal to 1, so the x component of the vector is -1, and x equal to 1. Oh, sorry, x is equal to 0 here, so there's no j component, -1, 0. So I draw this vector at this point. It says it will go -1 units along the x direction. It will go 0. There's no displacement in the y direction. So this is the vector at that point. So I continue the process for the rest 2 points. This point, -1, 0. So the vector at this point is when y is equal to 0, I component is 0. X is equal to -1, so this component is -1. So 0, -1. That means for this vector, I need to go -1 units along the x direction. So this is the vector. And the last vector at the last point, 0, -1, is x is 0, y is equal to -1. So -1. This is 1, 0. So this component is 0. So I need to draw a vector 1, 0 at this point. So this is how this vector field looks like at these 4 points. And part B show that every vector is perpendicular to the position vector xy. So what does it say? Every vector, this vector at any point xy, this vector is -y, x. To show that it is perpendicular to the position vector xy, how do I show 2 vectors they are perpendicular to each other? I use the dot product. Right. So I use the dot product of 2 vectors. If the dot product is equal to 0, that means the 2 vectors, they're perpendicular to each other. So I just need to dot these 2. So -yx is x, y. This is equal to -xy plus xy. See, it is exactly equal to 0. Okay, so if the dot product is equal to 0, that means every vector at the point xy is perpendicular to the position vector. Alright, so I'm going a bit fast here. So if you cannot write everything down, you can always revisit the uploaded notes on the e-class. So this graph shows some more representative vectors in this vector field. Like we only draw the vectors. At these 4 points, if we draw more vectors, you will see this vector field look like this. it seems like this vector field is spinning around the origin in the counterclockwise direction. Okay, so this is a 2D vector field. So let's look at some more examples of 2D vector fields. If the vector field is given by this function xy, the vector field will be looking like this. If the vector field is given by this function, x over square root of x squared plus y squared, y over square root of x squared plus y squared, this will be, the vector field will be looking like this. And if this vector field is y-x, or it is negative y-x, it will be looking like those. Okay, see, they give, according to different functions, you will see different kinds of vector fields in 2D. Okay, I'll stop here and continue on.